Hi all, welcome back. And in this video, we are going to learn about some special elements of Hasse diagram. So in previous video, we have seen about how to construct a Hasse diagram for a given poset and how to find the minimal, maximal, greatest, least element and the number of lines. So in this video, we are going to learn some of the special elements in a Hasse diagram. Okay, so let's begin this with a poset that is P, and here is a POR, partially ordered relation, defined on this poset. Okay, now first thing is the maximal element. So we already have calculated in the past video, but we'll see what these elements are and we'll see how to calculate them in this video as well. So first one is the maximal element. So an element M belonging to P, of course, is maximal. Okay, an element M belonging to P is maximal if there is no X, if there is no X belonging to P such that X M has an associativity with X. In other terms, you can say that M is has a partial order relation with X. Okay, so M and X, so there is no X belonging to P such that M has an associative with X. We already have learned about the associativity part. So what does it say is that M has an associativity with element X. It means that M is has a M and X are in a partially ordered relation, and M not equal to X. Okay, so this is called the maximal element because there is no X. This condition is not satisfied. Okay, so there is no X belonging to P such that M has associativity with X. Okay, so I think from this is a more formal of definition. We'll see what does that actually means. Before that, let's see what is a minimal element. So an element N belonging to P is a minimal element, is minimal if there is no X, if there is no X belonging to P such that, now it is opposite. So N is said to be minimal if there is no X belonging to P such that X has an associativity with N. Okay, so this is different and this is different, right? You got my point. So there is no X such that M has an associativity with X, and there is no X such that X has an associativity with N. Okay, so we'll see what does this means, but yeah, through some examples. Let's say we have to find some minimal and maximal element, and we have been given this particular hash diagram. So already you will be giving some hash diagrams. So here is A, here is B, here is C, and here is D, and you have to find the maximal and also the minimal. So we already know the minimal will include A because there is no other element in B, C, D which has an associativity with A. So A does not covers any element. Remaining element are covering A, but A is not covering any element, right? And similarly, we can find the maximal element out of this is D. Okay, so it was a simple part. Let's see another example. We have A here, and we have here B, and we have here D, and we have here C, and we have to find the maximal and we have to find the minimal. So maximal is, of course, if you see, for B and D, okay, so for B it's D, right? And for C it's D, and for A also it's D. So maximal is D. So there is no other element that is covering D, right? And for minimal, if we see, so minimal is obviously uh, A and C, because no any element is there which which is which these elements are covering. Okay, so minimal is A and C. So I hope from this too a little bit of idea you got. And let's see some more example like this, such that we have a set A, and division is defined onto the set, and it is a poset. And let's say what this A is. So A is a set containing elements like 3, 5, 7, 9, 11, 13, and 15. Okay, so these are the element, and division operator is defined on it. So first we'll be constructing the um, Hasse diagram for this. So let's say we have 3. Now let's say we take 5. So does 3 divides 5? No. So 5 will be there. 7, does 3 and 5 divide 7? No. So it's also like this. So 9. So 3 divides 9. So we will construct here 9. Okay, now we have 11. So we have nothing in 3, 5, 7, 9 dividing 11. Then we have 13. So it will be also like this. And for 15, so 3 and 5 divides 15. So we will construct it like this. And okay, so this is our diagram. Now if we have to find here the minimal element, so minimal constitutes of those element belonging to set A, such that there is no x that is associated with these elements. Like these elements are not being are not covering any other element. So minimal includes 3, 5, 7, 11, and 13. And what is the maximal here? So maximal is 9, of course, and 15. Out of 9 and 15, so any element is said to be maximal if it is from here you might see that 9 and 15 are the maximal. But just think about that. So are there any element that is covering 7 or 11 or 13? No, there are no elements covering 11, 17, 11 and 7 and 13. So these also will come under maximal. So 9, 15, 7, 11, and 13. Why? Because from the definition of maximal, so we have M belonging to P as maximal if there is no X belonging to P, such that M is such that has an associativity with X, such that M divides, here it is a division, such that M divides X. Okay, so there are no other elements belonging to this set, such that 7 divides that element, 11 divides that element, or 13 divides that element. Okay, so that is why this will come under maximal. So this is one unique example where we have something common in minimal and maximal. Okay, so let's come to the result. So from this I hope we are clear about maximal and minimal. So there are some results based on that. So first is, every finite poset every finite poset having the maximal and minimal element. For every finite poset, you can define the maximal and minimal elements in that poset. Okay, right? And the second result is infinite posets, where you are not aware of what is the final, what are the numbers in that poset. So for infinite posets, need not to be having the need not to have the maximal and minimal elements. Okay, so the infinite posets need not to have the maximal and minimal elements. Okay, so this is a very important point. So for finite poset, we can define the minimal and maximal element, but for infinite poset like z plus and less than equal to not z plus, it's just z. So if this be a poset, so for this, if we want to find the minimal, so definitely you can't find the minimum element for this, right? So it is infinitely towards negative and infinitely towards positive. So minimal and maximal for this does not exist. Okay, so this is a very important point regarding the minimal and maximal element finding for the poset. Now the second topic, second special element are greatest and least element. So we already have seen about this greatest and least element. So we denoted it by 1 and 0. So the greatest element for a poset is defined, denoted by 1, and the least element is denoted by 0. We already calculated, but let's define it formally first and then we will see. So these are the basic notations, right? So for greatest element, the notation is 1, and for the least element, the notation is 0. So keep this in mind because we might be using this part later on. So greatest element is 1, least is 0. Let's see what does that mean from this example. So let p, and let's define an operation. This is a por on p, and this be a poset. Okay, and an element an element G belong to P is greatest if there is an X that is being there is an X for G for every X belongs to P. So for every X belonging to the particular set, G X is covered by G. Okay, we can say that X is covered by G. So G should cover all the elements of P, right? This is very important. So if whatever operation you are defining, so for this operation, for every element, for this element particular, this G element, it has to satisfy this condition. We'll see what does that mean, but this is just a mathematical denotion. Similarly, we can find the least. So an element L belonging to P is least if X is having this comparison with Z for all X belonging to P. So every X belonging to P should cover this least element. Okay, so let's see this with example. It will be more clearer. So we have this Hasse diagram. Here is B, here is D, here is C, and here it is A. Okay, now if we have to find the greatest, so for here, if you find the greatest, so out of A, B, C, and D, the greatest would be covering all the elements. So D covers B, C, and A. So D will be our greatest element. And if we say least, so A is being covered by B, D, C, so A is the least. Okay, so we define it like 1 is D and 0 is A. Okay, let's see another example for this. So this is another example, and here we have elements like this, and okay, so it's B, it's A, it's D, and it's C. So here the greatest is an element that covers all the elements. So D covers B, A, and C. So D is greatest, but least, if you see, so which is being covered by all the elements. So A is covered by B and D but not C. So we can say that it does not exist. Okay, let's see another example. So we have this Hasse diagram already given to us, and we just constructed it as well. So 9, 3, and 15, and 5, and here we have 7, 11 and 13. If here we have to find the greatest, so greatest is an element which covers all the elements of the poset. So 9 does covers all the element of the poset? No. 15 does cover? No. 7? No. 11, 13? No. Okay, so for this it does not exist. And if we say that what is the least element, so does 3 is being covered by all the element, 5 is covered by all the element? No. So does not exist. So this thing keep in mind. Now based on that, we have two results like note. So here is this note that greatest and least element, greatest and least element, if exist for a finite set, of course, if exist, then they are unique. Then they are unique. Okay, so this is a very important result for greatest and least element, right? So right now we have seen four type of special elements. Now let's see another two special elements, and they are it's not a special element we say, but it is an important feature for this. So this is called upper bound and a lower bound. Upper bound, so an element is called upper bound and then an element is called a lower bound. Let's see what does that means in terms of this. So let P and this operation on P be a poset. Okay, and A is a subset of P. Okay, so we are considering one more feature, that is A, and A is a subset of P. So an element, an element U belonging to P is called upper bound, is called upper bound, or UB of A if X, okay, if X is covered by U for every X belonging to A. Now, here we are considering A as a subset of P, and we are checking all the elements of A, and we are seeing that whether X is covered by U. Okay, so this is important thing you have to note, right? And another part is lower bound of A. So an element L belonging to P is a lower bound of A, lower bound or LB of A if L is covered by, if L is covered by all the elements of A. Okay, sorry, this is important, right? Yeah, this is all. Next is we will be seeing some examples based on that. So let's see some examples. Let's see this example. And okay, so we have this P, and inside P we have 1 2 3. Okay, and 4 5 6, and we have here the poset, that is this. Sorry, let's define the relation onto that. So just a second, let me correct this part. Okay, right. Okay, now here is we are defining this less than equal to, so this is a poset. So this is a poset, and we have A is equal to 2 4. Okay, so if we have to define the upper bound of A, so the upper bound of A will be uh, any element belonging to this. So you have this diagram, something like 1, then 2, then 3, then 4, then 5, then 6, right? So like this, okay? So this is the hash diagram for this. Also, it is a tau-set. So yep, what we were saying, so this for this set A, if we have to define the upper bound, so any element that does cover all the elements of the set A. So any element, and that element has to belong to P. So any element belonging to P that covers all the elements of A, and that is 6. Okay. So here if we say that the upper bound of A, so 4 covers all the element of 4 3 2. 5 also covers all the elements. Okay, so 5 covers 4 2, and 6 also covers all the elements. So 6 covers all the elements like this. So we have 4 5 6, all the elements. It covers, upper bound includes all this. Because if we say 6, then we can't ignore 5, because 5 also covers 4, 4 also covers 4, so we have to take 4. Okay. And if we take the lower bound of A, so the lower bound of A should include all the elements which are being covered by this. So only 1 and 2 is being covered by this, so 1 and 2 will be the lower bound. Now out of this lower upper bound of A, we have to calculate the least upper bound, and out of this lower bound of A, we have to calculate the greatest upper bound. So greatest upper bound, greatest lower bound is 4. Okay. And lowest upper bound, lowest upper bound, lowest upper bound, it's lowest upper bound is see, greatest upper bound is 2, sorry, and lowest upper bound is 4. Okay. So this we can calculate from here, right? So yeah. So from here, for 2 4, 4 is the lowest upper bound, and 2 is the greatest lower bound, right? And if we take another set like 3 5, so for 3 5, if we have for A is equal to 3 5, let's say. So here if we calculate the lower bound for 3 and 5, it is 1, 2, and 3. And if we calculate the upper bound for 3 and 5, then that is equal to 5 and 6. So if we calculate the greatest lower bound, then that is equal to 3. And if we calculate the lowest upper bound, then that is equal to 5. Okay. So this way we have this upper bound and lower bound defined. So I hope I am able to explain all these special elements of hash diagram. But in case if you do have any comments or you do have any questions, then please do comment or post your comment in the comment section. I'll be happy to help. That's all from my side. Thank you.